So, in the previous we have discussed one example, that suppose we have set of vectors sin x, sin 2x up to sin nx, and that belongs to the, so in this case that belongs to the space of continuous function defined from minus pi to pi, and we want to check whether this check about linearly dependent or linearly independent. So, in this case what we need to do is, because for checking the linearly dependent or independent, I will take the linear combination. So, linear combination I am going to take. So, let us take it a1 sin x plus a2 sin 2x up to an sin nx equal to 0, where 0 is a 0 function defined in this interval. So, now in the previous lecture we have discussed that if I take the derivative and we n times, and then we will get n by n matrix. So, still we are unable to show that whether these vectors are linearly dependent or independent. So, here we are going to use some other property, and that is orthogonality. So, here we are going to use the property of orthogonality. So, in this case we know that two vectors are orthogonal when their inner product or the linear. So, suppose I have a vector v1 and v2, and till now we know that v1 dot v2, if it is 0, then we say that these two vectors are orthogonal to each other. But here we do not have the vector of this form, what we used to do, like we have a v belongs to R3 or R4, the Euclidean space. So, here we extend this orthogonality to the integration from minus pi to pi, and then taking function f(x) and g(x) dx. So, this or the concept of dot product becomes the integration from minus pi to pi f(x) dx, because here we have a vector that is of discrete type, but here we have a vector that is a function. So, if this is equal to 0, then we say that the function f(x) and g(x) are orthogonal to each other in the interval from minus pi to pi. So, here we are using the same property. So, now what we are going to do is, we know that from minus pi to pi, if I take sin nx and if I take sin mx dx, then let us check what is going to happen here. So, here we are going to discuss the formula for sin nx and sin mx. So, this formula can be written as half cos n minus mx minus cos n plus mx dx. So, here I am using the formula for the sign inequality, and now from here it can be written as half, then I taking the integration. So, it becomes sin n minus mx divided by n minus m minus sin n plus mx divided by n plus m, and then substituting the limit. Now, it is a n and m are the integers here. So, in this case I know that the sign n minus m will be some integer pi, so this will be 0, and similarly sign n plus m is also an integer value pi, that is also going to be 0, and similarly for minus pi. So, if you see from here, if I substitute the limit, then I am going to get half and then 0 minus 0, so that is 0. So, the dot product we are defined like this one. So, it is an inner product basically we are defined. So, in this case it is going to be 0. So, from here we can say that the functions sin nx sin mx. So, here we are considering one condition, that when n is not equal to m, because it may happen that when n is equal to m. So, if n is equal to m, then it is going to be the different thing, because when I take n is equal to m, then it will be sin square nx, and then we can very easily can integrate this one. So, the function sin nx and mx when n is not equal to m are orthogonal to each other in the interval from minus pi to pi. So, this one we can define. Now, from here, so let us use this one, this property. So, now I have a1 sin x plus a2 sin 2x up to an sin nx equal to 0. So, this is the equation we already have 1. Now, what I do is that multiply equation 1. So, here I am having the sin x. So, multiply equation 1 with sin x and integrate with respect to x. So, what I will get? I will get a1 integration from minus pi to pi. So, I am taking the integration from minus pi to pi, and x belongs to this one. Then it becomes sin x square dx plus a2 minus pi to pi sin x sin 2x dx and so on, and this is an. So, I can take my an outside. So, this is my an, and I can write sin x sin nx dx is equal to 0. Now, using this property, we know that sin x and sin 2x, that is going to be equal to 0. This is also going to be 0. So, all the terms will be 0 except the only this term, and this term from here you can see that I can write a1, and this integration you can, it can be written as 1 minus cos 2x divided by 2, and then doing the integration from minus pi to pi dx. So, definitely its value is not going to be 0. So, plus everything is 0, and that equal to 0. Now, from here you can check that this is a1 by 2, and then I can do the integration of this one. So, it is x minus sin 2x by 2, and substituting this integral. So, it can be written as a1 by 2. So, sin 2 pi and sine minus 2 pi, they are 0. So, I will get only here pi minus pi, and from here I can write down that it is 2 pi by 2 a1, and that is I am going to have a1 pi, and this is going to be 0. So, from here you can check that a1 is going to be 0. So, the first coefficient a1 is becoming 0. So, similarly, we can apply the same for other functions. That is, I can multiply. So, that is, we can multiply one with sine 2x and integrate between minus pi to pi. So, in that case also we will get a2 and all other terms will be 0, because here also we are using the property of orthogonality. So, from here I will get my a2 equal to 0. So, similarly, we can apply for all other functions, that is sin nx, n can be 3, 4, 5 up to n, and then from here we will get a3 0, a4 0 and an 0. So, from here we can check that in this case here all coefficients, that is a1, a2, a3, an, all are coming 0, and from here we can see that the function sin x, sin 2x, sin nx. So, this is a set is linearly independent. So, this is linearly independent set. Okay, so, from here we can check that this is the linearly independent set. So, this is we are done. Now, in the previous class we have also started this property. This is very useful property. So, I want to discuss this property again here. So, in this case what is we are having, that we have any finite subset of the vector space V containing a non-zero vector has a Li subset A such that this one. It means, suppose somebody gives me a set S and that contains suppose V1, V2, V3 up to maybe V100. So, it contains 100 number of elements, and somebody asked me to find whether it is Li or Ld. Okay, and then to find span. So, in this case it is very difficult sometimes to check whether the functions, whether this set is a linearly independent or dependent. So, then what we can do, we can remove from this set those vectors which are making this set S as a linearly dependent, because we know that if I remove a element which is also a linear combination of the previous one that we have already done in the theorem, then at least we can remove those vectors, and then we know that the span of S will be equivalent to that span of that vector, span of that set. So, these things we are going to do. So, this is very useful when we have a large number of vectors there. So, we have done this one. So, in this case my S is given to me. So, let we assume that V1 is not equal to 0. Okay. So, if the set S is linearly independent, then nothing to prove, because in that case the S is itself a, and from there the span of S is equal to span of A. Okay, so this is okay. Now so it is a case 1. Case 2, let S is linearly dependent, LD, and V1 we have taken that not equal to 0. Then using the previous theorem, so we have a set S V1, V2, Vn. So, what we are going to do? We are going to check, because V1 is not equal to 0. So, I can make a set like this one, S1 that will contain V1 only, S2 V1, V2, S3 V1, V2, V3, like this one. So, we can, because this is a linear independent, only one vector is there, then we can check whether it is linearly independent or dependent. Then we can check this is a linearly independent or dependent. So, then from there, using the previous theorem, we know that there exists a vector Vk such that Vk belongs to the span of the vectors preceding this one. So, that we have already done in the theorem, because it is linear dependent. So, from here we can find a vector, say Vk, which can be written as a linear combination with all the vector preceding this one. So, from here we can say that. So, then we can write a subset. So, we can write a subset maybe S1, that we can write V1, V2, Vk minus 1, Vk plus 1 up to Vn. So, we have discarded Vk, and then we left with this one. So, now if S1 is linearly independent, then S1 is equal to A, and we are done. But if S1 is linearly dependent, then we can follow the same procedure, whatever the procedure we have just defined, we can follow the same procedure. To discard some vectors, like we have discarded Vk, then again we can discard the vector which is a linear combination of the previous one, and so this way we can discard the vectors, whatever the vectors are there, and then in the last we get a set, we call it A, that is V1 up to this one is, which is linearly independent, and then we can say that the span of S will be equal to the span of A. So, this is the way we can use this theorem. So, now let us do one example of this one. Based on this one, we want to do one example. So, let us do one example. So, the question is, show that the ordered set. So, this is a set we are taking 1 1 0 0 1 1 1 0 minus 1 1 1 1. So, suppose this is my set S. So, I want to show that this set is LD, or maybe I can have a 2 more elements, maybe I can put 2 more elements, maybe I can have minus 1 1 1 and maybe 1 2 3 like this one. Suppose I take this vector, I just take 6 vectors and I want to check whether they are LD or not. So, the one procedure is that taking the linear combination, solving, and then we want to show that whether it is LD or not. Other thing is that it is an ordered set. So, we define a set S1 that contains the first element, and this is, of course, it is Li because it is only one element and that is a non-zero element. Then we define S2. So, S2 I am taking 1 1 0 and 0 1 1. So, I am adding one more element there, and then we want to check. So, from here now we can say that this vector and this vector both are linearly independent, because one vector cannot be written as a scalar multiple of other. Like I cannot write 1 1 0 cannot be written as a sum alpha times 0 1 1, because here the 0 element is in the third position and here 0 is coming in the first position. So, that is not possible. So, these are linearly independent. Then I take S3. So, S3 I will take 1 1 0 0 1 1 and then 1 0 minus 1. Now, from here if you see, I just calculate this value. So, this become a, so I will get a matrix that is 1 1 0 0 1 1 and 1 0 minus 1, and we can reduce this matrix into the echelon form. So, it is 1 0 1, I can make it 0 by multiplying. So, I can multiply minus R1 plus R2. So, it will be 0, that is 1, and it is minus 1 0 1 minus 1. Then I will again want to make this element 0. So, I will apply minus R2 plus R3. So, this is 1 0 1 0 1 minus 1, then 0 0 0, because these are same element. So, from here I can say that rank of this matrix, whatever the matrix is there, I just call it A matrix 2. So, infinite many solution. Okay. So, using this one we can say that my S3 is linearly dependent. So, when we have not added this element, it was Li, this was Li, but then we put this element, then the whole set becomes the LD. Now, from here I just check that 1 1 0 minus 0 1 1 minus 1 0 minus 1. So, 1 minus 1 0, 1 minus 1 0 and minus 1 and plus 1, that is also 0. So, it becomes 0. So, from here you can say that the third element, this one 1 0 minus 1 can be written as 1 1 0 minus 0 1 1. Okay. So, 1 minus 1 0 and this one. Yeah. So, from here I can say that the third vector can be written as a linear combination of the previous two one. Okay. So, from here after doing this one, now S3 is LD, linear dependent. Now, also S3 is a subset of S6, because S6 contains the sixth element, S6, or maybe I can call it S, not X6, let us call it S. And we know that if the S3 is linearly dependent and then the superset of this is also linearly dependent. So, using the property that superset of a linearly dependent set is also LD. So, from here I can say that S is linearly dependent. So, this way we can find out that it is linearly dependent. Now, next question comes from here, the same example, using the same example, find the largest linearly independent subset whose span is equal to S. Okay. So, in this case I just, for the calculation I just take, let us take S as, so I just take the first 4 elements 1 1 0, 0 1 1, 1 0 minus 1 and 1 1 1. So, I just take these elements, 4 elements. So, I want to find the largest linearly independent subset. Now, we know that S3 is LD, then we remove 1 0 minus 1 from the set S3. Okay. So, S3 was now becoming 1 1 0, 0 1 1, and it was 1 0 minus 1. So, what I am going to do, I just remove this one. Remove. Then I take the next set S4, 1 1 0 0 1 1, and then the next element is this one 1 1 1, and from here I just want to check whether this is linearly independent or not. So, now I can take 1 1 0 0 1 1. So, from here I just apply the same 0 1, because minus 1 I am multiplying. So, it is 0, and then 0 1 1, and then again I am applying here. So, it is 1 0 1 0 1 0 0, minus 1 I am multiplying, adding here. So, it is 0 and 1. So, rank is of this matrix is 3. So, S4 is linearly independent, and now this is, so we can say that S4 is the largest linearly independent subset of S, such that S4 span is equal to S span, because the element which was making the set linearly dependent, we have removed that vector, because that vector is not going to contribute in the span, and then we know that the remaining element will also span the same space as spanned by the set S. In the S, we do not care about whether there is Li or Ld, it is spanning some space, but after this one we have removed all these vectors which are making this set linearly dependent, and then after getting, we get the largest linearly independent subset, and then the span of S4 will definitely be equal to the span of S. So, this is the proof of this one. So, okay, let us stop here. So, in the today lecture we have discussed two examples based on the set of that how we can reduce the number of vectors in a linearly dependent sets, and then we can show that the span of the reduced set is equal to the span of the original one. So, in the next lecture we will continue with this. So, thanks for watching, thanks very much.